recording. Let's see if this works today. So I was not planning to talk about this, but I think actually this is a good time to talk about this. One of those things that maybe you just kind of pick up over time, but I think it's worth talking about explicitly. So, how to think like a functional programmer. Okay, so, how is functional programming different than other kinds of programming you've done? What are the ways that kind of work well thinking about writing Haskell versus other things? So, there's two main things I think I want to emphasize, and if you can get these drilled into your head, you're gonna level up in your ability to write Haskell code. Okay, so number one is always think about the types. Okay, we're gonna do maybe a couple examples in a minute, but I'll just say what the principles are, and then we'll talk through what they mean. Okay. Haskell's type system is there. It's a very strong type system. Haskell has very strong opinions about when things, match. And it's really there not to be like a burden on you or to, constrain you. Well, it is there to constrain you, but it's one of those things where constraints bring freedom, right? So this is a counterintuitive idea. People often think, oh, freedom means I can do whatever the heck I want. And that is one possible definition of the word freedom, but if you can do whatever you want, then you have to worry about everything all the time. And that's not actually a very free kind of feeling, right? Usually having some kind of constraints, you're actually within these constraints, I'm free to do whatever I want within these constraints because I know that they're protecting me or they're giving me some framework within which I can do stuff, right? So a lot of times people, there's lots of debates you can find on the internet about static versus dynamic type systems, and people are like, oh, static types, they get in my way, they just I can't be agile, I always end up having to cast things or whatever. Part of the problem is that the static type systems those people are probably used to are just not very expressive type systems, and so yes, they do get in your way because they can't express the things you're actually trying to do. Haskell's type system, it's not perfect, and there's some things ways in which you could be even more expressive than Haskell's type system, but for the most part, we'll see that it doesn't get in your way. It kind of allows you to say what you want. Okay, so always think about the types. And number two is think about what things mean, not what they do. Okay, what do I mean by that? Right, if you're writing an imperative program, right, the whole point is it's a sequence of instructions, and so you're thinking very operationally, what does this do? What does this do? How do I make it do the things I want? Okay? When we're writing a functional program, part of the point is we're not thinking about how to get the computer to do what we want. We're thinking about how to define the thing that we want, or how to say what it is that we mean, and then we let the computer figure out how to do it. It's I don't actually care. Okay, that's not, of course sometimes you do care, but at the high level, I don't actually care how the computer gets it done, as long as it can compute this somehow. And I shouldn't have to think about the messy details of how it actually stores things in memory and moves things around. I'm just saying look, here's the function I want to compute. Do it, right? So I want to do a small example, and we'll just think through these things kind of as a microcosm. Let's say I wanted to write a function. Let's say I was given the task to write a function called int_list, which increments every number in an int list. So let's write down our definition of int list here. Or you know what? We'll just use the standard Haskell. I'll just call it int list. a list of integers. Okay, so this is my task. Okay, what do you think is the very first thing that I should do? Yes, I should write down the type of the function, right? And now, Haskell can infer types of definitions. If you just write a definition, it can figure out what type it ought to have. But I think when people first defined Haskell, they were much more enamored of that idea than maybe they should have been. They're like, oh, it's so cool that it can like always figure out the types. But actually, always putting the types, even though you're not required to, right, is a very helpful way to think through what you're trying to do. And it helps the compiler give you better error messages. So yes, the very first thing, so step one, write down the type. So inc list. So what is the type? What do you think the type should be? List of integers.
Are we adding a certain number? Is it just one up one?
Yeah. So good. And this is exactly why this is helpful, right? Because as you're trying to write down the type, you're like, okay, wait, is it actually taking another integer, or am I just adding one? Like, right? It helps you clarify what you're trying to do. So no, my goal for this one, and maybe we could do a variant later, but it just literally adds one to everything. So what should this be?
I should just be able to get back the list.
Yeah, I agree. So we want to get back a list of integers. Okay. Okay. Good. Any ideas? What do you think step 2 should be? Okay, so yes, we'll get there, but I don't think that should be step 2 actually. So I'll just tell you, because otherwise I'm like doing this thing where I'm fishing for the specific answer I'm looking for. So looking at this second thing, right? So we already have a description of what the function's supposed to do, so that's good. If we didn't have that, then that's definitely one of the first things we should do, is write down, because like, and this would be the case if, say you're writing something and then you're like, oh, I need a helper function, right? So you go to make a helper function, you should definitely try to write down a precise description or definition of what it is the function is supposed to do, right? And like as precise as you can be, not just some vague like, oh, it's supposed to change the thing. It's like, okay, like try to write down a description that's not literally a definition, but is precise enough that someone else could come and implement it using your description. And that also helps you to clarify what it is. So we already have that. Okay, so that's good. So that would be step 2. I'll put that. Step 2, write down a precise description of what the function should do. We already have that. Okay, and steps 1 and 2, I mean, you often do them together, right? Because maybe as you're doing step 2, you realize you're like, wait a minute, that doesn't actually make, like the type I wrote doesn't quite make sense because I'm trying to describe what it's supposed to do, and I realized something that I'm going to need this extra parameter or something. So you can like, these can go back and forth, right? Step 3, this is sort of optional, but I think it's always a good idea. To help clarify step 2 is to write down some example inputs and outputs, right? So write some example inputs and outputs. So we could say, in our case, we would say inc list, I don't know, 257. What should that be? 368. Yeah. And we should always think about, and this is also a good time to think about sort of weird edge case and stuff. Like, what about the empty list? What do you think it should do if you give it an empty list? That's a list, right? What was that?
If you're adding one to nothing, I mean, or if we're interpreting this as like nothing, I guess you may just be a list of one.
So like this?
Yeah.
Okay. So what should?
Unless it's you have one element and 0.
Yeah, I mean, like, right. This should definitely be 1, but like, should this really be a list with one thing in it? Yeah, probably empty list, because like there's nothing to increment, so why would we like make up a number and stick it in there? Because we could also have negative numbers, right? So 0 doesn't even, there's no particular reason that 0 should be like the default integer, right? one other thing you could notice from this is you're like, oh, I guess it should have the property that the length of the output list should always be the same as the length of the input list, right? And that would also help clarify for us what this, what it should be in this case. There's not necessarily like a right or wrong answer here because, maybe you could just decide, no, the definition of my function is it does that, and if it's empty, then it outputs, a list with 0 or something. But you'll find that some descriptions are going to be more elegant and easy to implement than others, right? Okay. What if I have like same thing 3 times? I should still get 3 things out. Okay. And there's ways. We're not going to talk about this right now, but there's libraries you can use. Like you can turn these when you write down examples like this, you could like use some special notations. So they basically automatically turn into tests, so that it can like actually run them and make sure that they pass. I'm not going to do that, but okay. So step 4 is usually something like, so I think Andre was saying like the base case, right? But in general, we're going to pattern match on the input, right? Ink list. So what could it be? It could be, hang on. Can I still not do this? Oh, it's so annoying. I don't know. Okay. So it could be the empty list, right? Or it could be, a single element followed by some other stuff. Okay. Okay. So, and now we need to fill these in. Now, here's another place where this second point comes in. Think about what things mean, not what they do. Oh, the word do got. So here's the point where I think some of you, and I saw this working with several of you on the module 1. You might be tempted here to think about like, okay, well when you call ink list on a list, it's going to like recurse through and like then it's going to get to the empty list. So what do I need to do here in order to make that work? So that when it goes back from recursion, right? You're thinking in terms of like what it's doing and like how you need to define this so that it like does the right thing, right? But that's a very operational way of thinking in terms of what it does, right? We're just thinking about what it means. And actually, right, we already wrote down an example that says exactly what should happen when it's the empty list. So we don't need to think here, in this case, we don't need to think about like, if we got to this case through some kind of recursion. No, it's just like, what is ink list on the empty list? It's the empty list, done, right? That's what ink list means on the empty list. So that's the right answer. We don't have to think about how this might get used later. Okay, and then ink list on x cons x's. And again, this is a simple example, but I'm going to kind of go through it like you might if it was more complicated. Right? We might think at this point, well, I have to output, what type do I have to output? It's a list of integers. And it's not going to be empty, right? And because it needs to have the same length as the input list. So it's going to be a cons. So just thinking that far, you could write this. Be like, okay, I don't know yet what the actual things in the cons should be. I haven't thought about that part yet, but at least I know for sure I have to build a list. It's not going to be the empty list, so it has to be a cons. Now, of course, there's other ways you could make a list instead of, other than just literally writing cons. Like you could call some other function, or you could do something plus plus. But it's a pretty good guess in this case that when we're processing a list in order to return a new list of the same length, we're probably going to match up like empty list goes to empty list and a cons goes to a cons. So this is a very good guess, right? And this is the point where thinking about the types helps, because you're like, okay, so if this whole thing is a list of integers, and this is a cons, then what type goes in this? What type goes in this hole, and what type goes in that hole? And this is where I'm sad that my editor does not seem to be working. So, because usually it would actually tell you what the type of each hole is, right? I think you all saw that the other day. So for sure, if your editor supports this, then it may be able to do that. But even if it doesn't, if you load it into GHCI, it'll tell you. Says, okay, on line 23, column 18, I found a hole which has type integer. That's the first argument of cons, right? There's a lot of stuff here, so sometimes it can be intimidating seeing like these giant messages coming out of GHCI, but it's trying to provide you with helpful information. So if you like fight down the sense of panic, take a deep breath, and then carefully read through it, you might learn some interesting things, right? So this is telling you, this says, hey, I found a hole. It's an integer has to go there. And then it's telling you where the hole is, in case you weren't sure which hole it's talking about, right? It's like the first argument of colon, it was in this expression, and that in turn was inside an equation for ink list, right? And then it says relevant binding. So that means basically here's some variables that are in scope right there that are available to use that might be helpful, right? It's like, hey, you've got something called x's, which is a list of integers. You've got something called x, which is an integer. You've got a function called ink list, right, which is what we're defining right now, but you can have recursive functions. So, and then it's saying, here's something that would fit based on the type. You could just put x in there. That would have the right type. Now, that actually isn't what we want, right, because that would just like duplicate. But, and then let's go ahead. The same thing with the other hole, right? Blah, blah, blah. Okay, so what should we actually put in here? So what integer should go first in the output list? X plus 1, right? I think technically I do not need those parentheses, but I'm going to put them anyway. It depends on the precedence of plus versus cons, and I don't. If in doubt, use parentheses. And then what should go after this? What should be the tail of incrementing everything in x, cons, x's? Yeah, Paxton?
Couldn't we recursively call inklist on the rest of the list?
Exactly, I agree. Okay. And then as an aside, about recursion, but again, this fits into this second point, thinking about what things mean. This is a pretty simple recursion, but in general, right, if you're like, okay, this function is probably going to be recursive, you just say, all right, I'm going to make this recursive call, and I'm going to assume that it gives me the right thing. Most of you probably heard me say this like in another class, but you don't think about what that recursive call is going to do, like how it unfolds multiple steps. You just say, all right, I don't know what that's doing, but I'm just assuming that recursive call will give me the right answer. So inklist x's will give me x's with everything in it incremented by 1. And then the only question you have to ask is, what do I have to do with that correct answer to give me the answer to the original problem? So in this case, well, if we correctly get everything in x's incremented, all we have to do is stick x plus 1 on the front, and that's our answer, right? And by the magic of induction, that it will be correct then, because this is assuming this is correct. It would be like your induction hypothesis in a proof by induction. You say, if I assume that it's always correct for x's, then it's going to be correct for one more thing on the front of x's. We will talk a lot more about induction and what it has to do with functional programming later. But any questions on this at this point? Yeah, Garrett.
Do we need a case for single element, or is that covered with the cons?
What do you think? It's a good question. So do you all hear Garrett's question? He's asking if we need a separate case for a list with one element.
I think it's covered with the second case, because if you break off the first element and there's nothing in the second half, it's just going to link to
Right.
that empty list.
Right, exactly. exactly right. Yeah, so X's could be the empty list. And then in which case, yeah, this would be a list with one thing, and that would do the right thing, because it would give us X plus 1, and then we'd call ink list on that empty list, which would then be this case. So, yep. Yeah, fundamentally, right, because lists are defined as, there's two possibilities. It's either empty or it's a cons. Fundamentally, if you're processing a list, you're going to need two cases, unless there's some special reason that you need a special case for something, right? So, like on Module 1, when you're looking for runs, right, maybe the way you wrote your functions, you might need some extra cases because, you actually need to look at the first two elements because you need to compare them or something like that, right? In that kind of case, then you're going to need more cases. But if we're just doing some kind of simple processing of a list, yeah, that's annoying. Okay, so can hang on a second. Let me make sure I don't show you anything I shouldn't. I'm going to kill teams, and then, all right. Cool. Excellent. Any other questions? All right. So we are going to start talking about something today that on the surface might seem like I've suddenly jumped to a completely different topic, which is to talk about propositional logic and proofs. And so, those of you who've taken discrete with me, we've talked about propositional logic. We're going to look at it from a slightly different perspective, though. So some of it will be familiar, but we'll quickly get to stuff that is presented in a different way, and we're going to see these things kind of come together over the semester. And part of the reason that I'm doing it this way is that, so actually, functional programming can be used for lots of things, right? It's used in many, many areas, but one area where it's used a lot is in cases where you need some kind of higher level of assurance that the code that you're writing is correct or conforms to some kind of specification or doesn't have bugs. So actually, Silas and I were just talking about this the other day. We were talking about why functional programming is used a lot in blockchain applications. It's used a lot in finance in general. So, if a bug in your program means you could lose $1 million, you now suddenly have a big incentive to make sure that it doesn't have bugs, right? Not that functional programs don't have bugs. Obviously, you can write bugs in any language, but as we'll see, there's good reasons why this kind of language, and especially when you couple it with a strong static type system, there's a lot of things you can express and basically be assured that as long as you trust, say, the type checker, or as long as you trust the compiler, your program will not have, right? It mathematically, basically, running the type checker kind of amounts to proving mathematically that your program satisfies certain properties or doesn't have certain kinds of bugs. Okay, and it's the fact that that's possible is really one of the coolest achievements / coincidences / discoveries in terms of math and computer science of the 20th century, and it's so it's something that I want to show you, and it's the kind of thing that as you go on in your career, whether or not you specifically go on to write code in a functional language, there's lots of languages that are requiring features from functional languages, and there's a lot of people that are thinking about these kinds of things with formal verification of programs and stuff. So it's cool, and it's also can be practically useful to know. All right, so I need some chalk. Didn't think to bring my chalk. Oh, not even chalk here. Oh, there's some up here. All right. This chalk is kind of crappy, but. Okay, so first, I need to talk about inference rules and proof systems. So this is basically a specific, oh, that's actually purple. Wow, okay, that's weird. There's a specific notation that we often use to write down things called inference rules. I guess, oh, okay, all right. So, here is an example of an inference rule. It looks like this. We have a line in the middle, and we have like, you know, we have some premises up here, and we have some kind of conclusion down here. Right, so this means, you know, if A and B and C, then D. Okay, so it's really just a fancy way of writing an if statement. Okay, and an if specifically in the form of if, you know, the and of a bunch of things, then some conclusion. Okay, and we think about this in terms of like, maybe you think about it in terms of like what you know or what you can prove. So like if we know A, B, and C, then we can conclude D. Or if we can prove A, B, and C, then we can prove D. Okay. So let's do a very simple example. Okay, and if you have like a collection of these things, it could make like some system under which you can conclude certain things or prove certain things. So here's an example. So let's say I've got like B, what else do I want? I want no. Okay. So this is an example of a simple system of inference rules. This one here, I don't know, anyone, any guesses? What do you think this means? Andre? Yeah, it just means A is true. So this is what we call an axiom. Because it doesn't have any premises. So there's nothing you have to satisfy before you can conclude A. Okay, so this just means, yeah, A. Right, and this means like, you know, if you know A, or if you can prove A and you can prove C, then you can conclude or you can prove B. Okay, so A is, we can prove A for sure. Can we prove B? Yeah? Why?
A and C, and if A and C, then B.
Right. Oh, right. So if A, then C, and then, right. Exactly. So, I'm going to put this up here. So, you know, we know that A is provable. So here is a proof of B. And here's the way that we often write down proofs. We write them as trees. Okay, so I want B to be the thing I conclude at the bottom. Right, and I have a rule here that says, well, and actually, you know what, I'm going to like number these. This is rule 1, 2, just so that when I put them over here, we can like keep track of which ones we're using. So this is 5. So rule 1 says, right? If I can prove A and C, then I can prove B. Well, how do I prove A? I can prove A using Rule 2. Rule 2 says you can just get to, and so I just put that here. Okay. C, I have one way to prove that, which is Rule 3. But in order to prove that, I need to prove A. Right? Well, in order to prove A, I can use Rule 2 again. Okay, and then so I now have this tree that, at the very top, the only things I have are all axioms. Right? There's nothing like left that's dangling that I haven't finished. And the thing at the bottom is D, so this is a proof of D. Okay, I mean, using the rules in this system. So maybe, like in 8th grade geometry, you were taught that a formal proof is like a list of statements where each statement only depends on previous statements or something like that. Okay, that's not true. Proofs are actually trees. And really, that's what was happening. Even with, like, you could write it in a list, but each thing like depends on previous things. So you could have actually written them in a tree, where like each thing kind of depends on the things above it. Okay, we can definitely prove C. Can we prove D? I see some yeses, I see some nos. Should we fight? Anyone want to argue for yes or no? Yeah, Jack.
I think we'll be yes and no, because if D is true, then E will also be true, and vice versa, since we know that B is already true.
Right. Okay, we can definitely prove B, right. And so, yeah, if I can prove, like in order to prove D, the only way I could prove D is if I could prove E. Right? The only way I could prove E is if I could prove D and B. Well, we know we can do B. But then I'm back to having to prove D. So, it actually depends on whether we allow infinite proofs or not. Right? Because I could make an infinite tree that just goes D, E, D, E, D, E forever. And like, if you're cool with that, then I guess that would be okay. But we're generally going to say no. Proofs have to be finite. So we can't prove D or E since there is no finite. Okay. Cool. Okay, so I mean, in general, when we write down proof systems with inference rules, we're going to have much more interesting things here than just like letters. But this is just an example to, to see kind of the basic idea of how these how we write them and then how we kind of put them together into trees that are proofs. Yeah, Jack.
So if we did have infinite ones, would it be true?
Would
the ED thing be true if we could use infinite?
Yeah. Yeah, if you allowed infinite proofs, then you could make an infinite tree which has D at the bottom, and like everything matches up in the tree and it just goes off to infinity. And if you allowed that, then yeah, that would be a valid proof of D. So like, what if we had another thing like, well, so like what about F? I can't prove F because there's no rule that lets me prove that. But like I could make a rule here that's like, to prove F, you have to prove A and Q, right? Well, now there's a rule that lets me prove F, but I can't prove Q. And so in this case, I also couldn't prove F, no matter whether I allowed infinite proofs or not, right? D and E is kind of a weird case where they kind of imply each other, so yeah. But there are interesting cases where allowing infinite proofs makes sense, but we're not really going to talk about them in this class. So. Cool. Any last questions? All right. So next time we're going to start talking about actual propositional logic, like and, or, not, all that kind of stuff that you probably are familiar with. But then we're going to recast it in kind of this form and think about what that means. All right. See y'all on Friday. So the module 2 is posted on the website, by the way. So.